March 13, 1989. It was still winter in Canada. Snow blanketed the cities, and the temperature hovered below freezing. At 2:44 a.m., without warning, the entire province of Quebec went dark. Lights flickered and died. Power plants shut down. More than 6 million people were suddenly without electricity. No heating, no communication, no running water. The culprit? Not a cyber attack, not terrorism, not human error. It was the sun. Just hours earlier, the sun had released a massive coronal mass ejection, CMAO, launching billions of tons of plasma and magnetic energy toward Earth. Traveling at over 2,000 kilometers per second, the waves slammed into Earth's magnetic field, generating powerful electric currents across the planet's surface. In Quebec, those geomagnetically induced currents, GICs, surged into the regional power grid, overloading transformers and tripping protective circuits. In less than 90 seconds, the entire grid collapsed. Across the province, elevators stalled, traffic lights went dead, radio towers fell silent, and emergency services were paralyzed. At Infinity Beyond, we emphasize that this wasn't just a freak event, it was a preview of the future. Quebec's blackout demonstrated just how quickly space weather can overwhelm our infrastructure. Despite its modern electrical system, the province had no defense against a geomagnetic storm. And Quebec wasn't the only region affected. Northeastern parts of the United States also reported electrical anomalies. The only reason they didn't face full blackouts was that their grids were better interconnected, able to absorb and redirect the surge. But what if the storm had been just a bit stronger? Experts later warned that a more intense storm could have caused permanent damage to transformers, not just shutting them down temporarily, but melting them from the inside out. Replacing these massive units can take months or even years, especially in remote regions or during widespread failures. In a worst-case scenario, large portions of North America could have remained dark for weeks, plunging society into economic chaos. And that was in 1989, before the internet became the backbone of global communication, before cloud storage, before GPS-controlled agriculture, aviation, and finance. Today, the risks are even greater. As solar activity increases during solar cycle 25, scientists warn that power grids around the world, especially those in higher latitudes like Canada, Scandinavia, and Northern Europe, remain extremely vulnerable. In fact, some countries have begun to upgrade their transformers and implement protective switching systems that can disconnect sensitive components in the event of a solar storm. In the United Kingdom, for instance, the national grid has begun replacing older equipment and developing contingency plans. In the United States, agencies like NOAA and USGS monitor solar activity in real time, issuing alerts to grid operators when high-energy events are detected. But these systems are only effective if there's advance notice. A fast-moving CME, like the one in 1989, can give us less than 24 hours to prepare. At Infinity Beyond, we explore these fragile connections between the cosmos and our civilization. The blackout in Quebec was just a warning shot. As our world grows more reliant on digital systems, a single solar storm could bring it all crashing down. In the next segment, we'll investigate the near miss of 2012 in more detail, and what would have happened if Earth had been just a few degrees closer in its orbit. Because one thing is certain, the sun has no politics, no preference, no mercy, only power. July 23, 2012. A date that should have gone down in history, but instead became the greatest near-miss humanity has ever experienced. On that day, the sun unleashed two of the most powerful coronal mass ejection CMEs ever observed in the modern space age. These outbursts didn't just burst, they collided with one another in space, forming a supercharged cloud of plasma hurtling toward Earth's orbit. Had this event occurred just 9 days earlier, Earth would have been directly in its path. According to a joint NASA and University of California study, the storm's strength was comparable to the Carrington event of 1859, but its speed and energy output were even more extreme. The CME traveled at 2,850 kilometers per second, one of the fastest solar storms ever recorded. Fortunately, Earth was on the opposite side of the Sun's rotational alignment at the time. That simple timing, pure cosmic coincidence, may have saved modern civilization. At Infinity Beyond, we often ask not just what happened, but what if? If Earth had been struck directly, the impact would have been immediate and devastating. Satellites would have failed across every orbital layer. GPS signals, relied on by airlines, shipping companies, agriculture, and global logistics, would have been severely disrupted or lost entirely. Navigation systems would go dark. Communication satellites would fall out of sync. Even the International Space Station may have had to enter emergency mode. And that's just above the atmosphere. On Earth, transformers across power grids in North America, Europe, and Asia would have faced saturation from geomagnetically induced currents, leading to overheating, breakdowns, and in worst cases, explosions. Local blackouts would cascade into continent-wide failures. Water pumping stations, ATMs, hospitals, and data centers, anything that relies on electricity, would be paralyzed. But it doesn't end there. The Internet itself, especially its undersea cable network, would be vulnerable. While optical fibers are generally resistant to electromagnetic interference, the repeaters, electronic devices that boost signals across long distances, are not. A storm of this magnitude could compromise the Internet at its physical core, leading to a global Internet outage lasting weeks or months. Economists estimate that the global financial loss could have exceeded $2 trillion in just the first year alone. Insurance giants may collapse under the weight of claims. Supply chains would stall. Markets would crash. And even food distribution would grind to a halt in urban centers where logistics rely on just-in-time systems. In short, society would reset. And here's the most alarming part. The 2012 CME went almost entirely unreported in mainstream media. Only scientists and space weather agencies fully understood its scale and consequences. The general public remained unaware of how close we came to disaster. No headlines, no emergency meetings, no global response drills. At Infinity Beyond, we shine a light on these silent warnings. The sun doesn't just give us life, it holds the power to take it back in an instant. The 2012 storm was not an isolated event. It was a glimpse into what could and one day will strike again. In our next episode, we'll dive into the solar flare classification system from B to C to the terrifying X class and explore how scientists rank the energy of the sun's tantrums. Because in the language of stars, X marks the spot where technology meets extinction. To better understand and track solar storms, scientists use a classification system to rank solar flares. Intense bursts of radiation from the sun's surface. These are divided into 4 primary classes: B, C, M, and X, with each letter representing a 10-fold increase in energy from the one before it. B-class flares are the smallest and weakest. C-class flares are minor, often undetectable without scientific instruments. M-class flares can cause brief radio blackouts at Earth's poles and minor radiation storms. But then there's X-class, the monsters of the solar world. X-class flares are the most powerful explosions the sun can produce. And even within the X-class, scientists use a numeric scale from 1 to 9 to rate severity. An X9 is far more dangerous than an X1. In fact, some solar flares exceed even X9, entering extreme, rarely seen territory. At Infinity Beyond, we explore why these numbers matter more than ever in a hyper-connected world. Let's put it in perspective. The Carrington event of 1859 was estimated to be around X45, by far the most powerful flare ever witnessed by humankind. It released enough energy to power the entire modern United States for over 1 million years. The 1989 Quebec blackout was caused by an X1.4 class flare, and the near miss in 2012? It was likely between X20 and X28. These aren't just data points, they're a countdown. The power of an X-class flare lies in what it carries: radioactive particles, X-rays, and extreme ultraviolet radiation. These emissions move at the speed of light, meaning we receive zero warning. When such a flare erupts and is Earth-directed, the effects are instantaneous, causing radio blackouts, communication failures, and GPS disruption within minutes.